so the 36 beneficiaries of the Ashley project, and we've got external attendees. So this is a special event. You will have an overview of the first results we've produced in the project, of the topics we're addressing in this European project. And I would first like to welcome you. The meeting will be all the afternoon, and I think that you will have this opportunity to exchange. Feel free to ask questions to the members of the consortium and you, participants, of course, to exchange your ideas and your views of, in the IMA domain with our external invitees. I am Thierry Marais from Thales Avionics. I am the coordinator of this European project, and I will be assisted by ISQ in charge of the dissemination aspects in this European project. So I consider that this event is now open, and I will leave the floor to Marina and Margarida. You will introduce yourself, and you will present the objectives of this academic workshop. Thank you.
Thank you. Thank you, Thierry. Good afternoon to everyone, particularly to the newcomers. I would like to thank you very much for accepting the invitation to be here. I would like to thank particularly to Ingemar that has organized this invitation to the Linköping universities to come here and with representatives to share with us their developments and also to give us the opportunity to show you and share with you what we are doing here in Ashley. Well, my name is Margarida Pinto. I come from Portugal, ISQ, and we are the dissemination manager for the Ashley project. I would like to present you my colleague, Marina Almeida, is also involved in all dissemination activities, and she has been in charge of organizing this academic workshop. So I would like also to thank Ashley Partners for staying here during the afternoon and also for participating and collaborating with us in this specific event. Take the opportunity in the coffee break to meet them and to talk with them and discuss relevant topics and items that you would like to see more clarified. This is the program. We will start by presenting you what is the concept of these academic workshops with Ashley. And I will do that myself. And then we will have the presentation of the Ashley project. All this information will be available at our project website that you can accede and check periodically what is new there regarding the project developments. And then we have a package of technical presentations shared by Ashley Partners and also by our invitees that accept to be here and to present us some developments. So regarding the concept of these academic workshops, so it's mainly, it's not taking? Oh, okay. The specific objectives of this academic workshop, what we called Meet to Ashley, is in fact to share internally in first stage the developments, the scientific and technical developments of the Ashley. This is very important because sometimes in large projects like this one, the research partners and industry sometimes are not really connected in terms of scientific developments that are of interest to the project, but it is the background of it. So we decided in this project to have a dedicated event that we could, the research institutes and academia in the project could show to our industrial partners these specific developments and scientific issues that are of relevance and just for them to be aware and discuss and exchange ideas about it. Additionally, we also thought it would be very good to have other academic representatives from local universities, where we have our P1 reviews, because these events are really held together with the project reviews with the European Commission, as Thierry mentioned. And together with that, we can create a database of these researchers and students from universities that can share with us during all over the project our developments and get also contact with industry that is involved in the Ashley project. So this is the main concept of these academic workshops. How do we work? So you can see the partners of Ashley that come from university and research centers and also from industry. So you have here an idea of what are the typology of partners that you have in the project. And that was the main motivation to have this internal dissemination workshop. How do we work? So this event is organized together with the project reviews. Event program involving also Ashley partners and academic representatives from local universities. So it's not really only provide you information about Ashley, it's getting also information from you and exchange ideas. This event is being recorded. So back there, there is a person that is recording the event. The speakers are aware of it, and we have permission of them to just be recorded. Why? Because we want this event to be disseminated in social networks, particularly in YouTube, for young students to see and get motivated by this presentation. So do your best to make animated presentation and to gather more engineer students for this area of avionics, because it's really difficult to gather these engineers all over Europe. So it is an important goal from the European Commission to motivate engineers for aeronautics, and in particular for difficult topics of some complexity like avionics. So do your best to be animated and to promote this kind of action. And of course, all presentations with the permission of the speakers will be available at our project website, which I'm going to show you. You have here the address, and there you can find a lot of information, and the presentation will be publicly available. So, finally, the program. I thank you all again. I'll be here as well. The coffee break. At the coffee break, you have outside there what we call the marketplace, which is a specific dedicated, event that we have posters with partner products and also project developments. We don't have too much developments here now because we had just had 1 year of the project, but you can see some products and concepts that are being used in Ashley. And you can discuss with all the Ashley partners that are here these details that are presented there. We have 15 posters, so a lot of information is included there. So please, we invite you in the coffee break to go there and just go around and see these posters. So I will start by inviting Thierry to present Ashley. Yeah. And just to give you what is all about this project. Thank you.
Thank you. That will be a short presentation because not everybody is aware of what Ashley is. Ashley is a European project you are not all involved in. So we'll have a first overview, Ashley at a glance, let's say. Yeah, on the table. No? Let's start with the name of the project, Ashley. It's a very long acronym, and the keywords are avionics systems. So this is an aeronautics project, of course. Avionics system hosted on a distributed modular electronics large-scale demonstrator. So distributed modular electronics, that's a concept that's been defined, investigated in the previous project that was called Scarlet. So I will explain a little bit what distributed modular electronics is. So we're talking about a large-scale demonstrator. You will have an overview of what we are investigating in those demonstrators that will be connected in a large-scale demonstrator. And finally, it is for multiple types of aircraft. There is not only one airframer represented in this room. We've got various ones. Airbus, Dassault Aviation, Saab, Alenia. So it's not just for one type of aircraft, it's for several types of aircraft. And we call that project Ashley. It's 42 months long, let's say 3 years and a half. And it's been started 1 year ago now. And it's around 40 million euros. So that's it. Ashley, avionics system hosted on a distributed modular electronics large-scale demonstrator for multiple types of aircraft. And I would say Ashley, that's shorter. How many countries are there in this consortium? Almost all Europe, but more than Europe, because we've got also Russia. So 13 countries are represented and many beneficiaries, many partners in this consortium. I won't mention all the countries, you can see them. And many beneficiaries, many partners, 36, that's a large number. And we've got, of course, airframers, the industry, aeronautics industry, research centers, universities. That's the reason why we've got universities present in this meeting room today, and small and medium enterprises as well. We can't work without all those partners in this consortium. If we want to summarize in a few words the purpose of Ashley, I would say that it is about integrated modular avionics, what we call IMA. So this concept has already been used in previous programs, aircraft programs, and we would like to work on a new generation of IMA to address the future aircraft programs. And we will work on the results coming from previous or ongoing studies, projects. The main results will come from Scarlet. That was the project funded by the EC in the past, before that one. But of course, we will rely on the results produced by national collaborative research projects funded by many countries in Europe, and of course, other European countries. And the purpose is to achieve a demonstration of what is the most advanced technologies available today in aircraft-level platforms. And you will see that the demonstrators are under Airbus responsibility for most of them, or Dassault Aviation's responsibility, because we want to have aircraft-level platform. This slide is to explain where we come from and where we are going to. On the left, you see the past, but still existing federal architecture, where each system was implemented and hosted by a dedicated hardware with a dedicated software, and each function had its own, of course, system designer, and the system designer for each function was at the same time the function supplier and the module supplier. So this federated architecture had limits. And what we call line repressible unit is the module hosting each function. So we've moved, a few years ago, we've moved with this IMA concept, integrated modular avionics concept. That was the first generation with the A380 from Airbus. That concept had been reused in other aircraft programs as well, where now we've got several functions in the same module. So that's much more complex to manage. So now the module has a new name. That's what we call line replaceable module instead of line replaceable units. And the fact that we have to manage several functions in the same computer, let's say, that brings many additional constraints. So for the same module, we've got the function suppliers involved in the design, the module suppliers, but of course the system designers, and everything has to fit in the same, within the same box, with the same constraints. And to say in a few words, you have CPU and the input-outputs in the same block, in the same box, an operating system, and the functions. So this is already implemented. That's the first step. But we want to go beyond that. We would like to go from this first generation of integrated modular avionics to the future's second generation. So we've already worked in this direction, but that's not finished. So as you see, between that is currently used and that, there are some differences. In particular, there you've got the IOs, and the IOs have been extracted from the modules. Now in the modules you've got the CPM, the CPU part, and the input-outputs have been separated from the modules. There we had, for instance, 2 providers for the CPM, the core processing modules. We have 2 providers. For the input-output modules, there are 7 providers. And you can imagine the number of combinations we can have. And in this first generation of IMA, we've got 7 different types, no, I don't remember, many types, 7 types of different modules. If you separate the IOs, you will simplify and you will reduce the number of modules, of CPM modules. And you will have many benefits that I will present. So distributed modular electronics is a new concept that was already introduced in previous projects, and we're going to go on with that. So if we come back from that to that, as you see, we have separate input-outputs. They are not in the computing modules. So that has some main advantages, benefits, that if you have the input-outputs close to the actuators and to the sensors, you will reduce the number and the length of the wires of the cables. So that's a main benefit in an aircraft because the way is critical in an aircraft. So the first step was to separate the IOs, to put those IOs close to the sensors and the actuators. So through, for instance, what we call the remote data concentrators. And then the processing is still in an avionic bay, but we just have to communicate with the AFDX bus. And all those wires are very short length because they are close to the actuators and the sensors. So that was the first benefit. We reduce the cable length. As a consequence, you simplify the other modules, the core processing modules, and you will reduce the number of types of modules. And that's more, that there is a benefit in terms of scalability as well. The next step would be to increase the capabilities in terms of computation. So increase computing module performance to host more functions in the same module. So you see there 1, 2 functions. And if we increase the computing module performance, we can host much more functions in the same module. So the idea is to have more generic modules, less types of module, to host more functions. And we've already identified 3 types of modules. That may be enough. Let's say modules dedicated to time-critical applications, modules dedicated to high-performance applications, and another type of module dedicated to, for instance, data distribution server. There you see that we can have common spirit that can be used by several functions. So I will explain it. So we have the modules with the computing resources. We have the operating system. But another idea that was investigated in the past was the introduction of platform-level services. Platform-level services between the functions and the hardware and the operating system. So what do we mean by platform-level services? An example would be a data distribution service. So with this type of architecture, with this intermediate layer, in fact, you enhance the portability of the functions of the applications. It's easier to integrate those functions in the modules, in the systems, because the implementation of the data, for instance, is hidden. It's no need to know how it is organized, where the data is located. You just have a single service to access the data, and the application will be simplified, and it will be better to distribute the applications and the functions in this distributed architecture. So that's typically a topic that we will address in the Ashley project, where we're going to work on middleware, database distribution service, for instance. So, as I was mentioning there, you see that we can have spare, no function running. That can be used for reconfiguration mechanisms. Of course, there is always redundancy in the aircraft for safety reasons. But if we can have reconfiguration mechanism in the overall architecture, we can take benefit of this distributed architecture to have spare that is common to many functions. And if that core processing module fails, then we can reconfigure the module to transfer all those functions in that core processing module. That's what we see there. But if another core processing module fails, we will translate and we will reconfigure the modules as a consequence. Yes?
From your picture, I wasn't sure. Do you mean the configuration mechanism should be in the middleware or in the application?
That was studied in Scarlett. Who has the answer? I was not in Scarlett, but is the reconfiguration mechanism, are they implemented in the platform level services, in the middleware, or somewhere else?
The configuration. So we have clarified this. Unfortunately, the French colleagues are not here.
I can imagine both. I just wondered if
It has been done in the configuration. We have position or configured for 2 positions and automatically switch over when the other position is used for the module. So if, for example, by a failure, one position is not valid and not usable, they switch over to another configuration in another module.
so this mechanism is entering the application for you?
No, it's just a configuration item. What has been configured, the application is the same. Because we have these APIs, RN 653, and therefore we do not need to adapt the application.
Thank you, Eric. So we've already worked in the past on those reconfiguration mechanisms. We won't address them again in Ashley. We have additional things to investigate or to de-risk, but that's part of the path towards the next generation of IMA. Something else that was that is new compared to the first generation of IMA is what we call this integrated platform toolset. And that's typically a topic that we're going to address deeply in Ashley. What do we mean by integrated process and toolsets? It's a global framework of tools, consistent tools that allows to manage the overall process for developing, integrating, evaluating, assessing, verifying all the systems, the functions distributed over the hardware. So what's the purpose? What's behind that? It is a model-based approach. That's a thing we discuss a lot in Ashley. So model-based. We want to, of course, allocate all those functions, all those applications onto the overall platform resources. So many resources are shared in terms of core processing, and remote resources are shared by many functions. So the systems and the applications are distributed, and that has to be prepared well in advance thanks to modeling and tools that will be integrated in a big framework. And that's one of our topics in Ashley. And of course, that will enable early validation. And early validation, in the end, will become maturity. So we want to improve the maturity at the entry into service. We want to have much maturity, more maturity than in the past. So the A350 will be more mature than the A380 at the entry into service, but the next programs will be even more mature. Or the same level of maturity will be reached much more before what we had in the past. Another aspect that is considered in this type of research, of study, is the scalability. So the scalability, in 2 words, is the capability of the architecture to be adapted to various aircraft types and to a large number and many types of applications. Applications, different categories of application, high-performance application, time-critical applications, avionics server functions. And IMA2, IMA1G, this kind of architecture can host few functions and was more focused on one single type of aircraft. And the target is to host much more applications and functions and varied types of functions in this architecture, but also at the same time addressing not only one family of aircraft, but several families of aircraft. So that can be mainline, regional, large or small transport aircraft, or bizjets. So typically in this consortium, the size of the aircraft manufactured by Dassault Aviation is not the same as the aircraft produced by Airbus. That's obvious. But the technology we tend to investigate and in the end to produce, to develop, and to certify, the idea is to use the same modules, the same things. So where do we come from? Here is Ashley. Here is our target. IMA second generation for the future aircraft programs. Between the second generation and the first generation, so there have been several research projects. One of them was Scarlett. The IMA first generation, I can't read it, but so we have, of course, the A380, Airbus A380. We've got the Airbus A400M. That technology has been used by ATR. In the meantime, there was the A350, Airbus A350. So that was a step forward. That was not the IMA first generation. That was not the second generation. That was in the middle. And now we are going to work towards the IMA 2G. So key challenges are industrialization, modularization, integration, services certification. So Ashley, this project is the path of future EMA 2G-based aircraft programs. And all future aircraft programs will be based on the IMA, of course, and much more functions, scalability, security, safety, etc., etc. The fields we are addressing are in red. Some examples of previous or ongoing projects, that's not exhaustive. I've mentioned there in middle Scarlet, and these are topics of interest for such IMS studies. So, of course, we try to de-risk and to reach higher level of technology readiness level for the core resources, so the core processing, the network resources, the remote resources. We addressed in the past the installation and the packaging. We work on services, platform services. But we'll be focused in Ashley on configuration process and tools and framework. We were talking about this integrated framework too. We will address the applicative middleware. One example will be data distribution services. We will work on support, training, and of course, the main part will be platform or function architecture. That's the scope of our project. Some objectives, I will just mention some of them. One is to decrease the overall design time when we design avionics functions. So that's maybe through, thanks to more integrated tools. So reduce design time. Time is money. We would like to work on the open world. It's not the avionics domain. So we've been focused in the past on the avionics domain, but there is another domain that is the open world. And we would like to investigate the interfaces between the avionics domain and the open world domain. We will assess the use of photonics and smart technologies, smart sensors, smart actuators. So we will try to use those technologies in our demonstrators. And in the end, the demonstrations will be focused on aircraft functions and applications. And we will also address middleware aspects such as the database services, data distribution services. An example of use that we can have of those technologies in an aircraft is illustrated by this slide. So it's about the avionics database distribution service that can be used by functions such as flight management, airport navigation, flight warning, maintenance. So the idea is to integrate such a technology to exchange avionics data in this distributed architecture, but having in mind performance, safety, data integrity, fault tolerance. An example would be to share static databases, example of databases and the navigation data, airport maps that can be used by several mission functions, such as flight management or airport navigations. But that can also be used by the flight warning. Flight warning generates some errors messages. If we store those messages in a central database, if you remove the equipment that is hosting the flight warning, the messages will remain in the system on board the aircraft. So that can be trivial, but that's not existing yet in the aeronautics. So that could be a benefit, or that is used in the maintenance domain. So this demonstrator is led mainly by Airbus France Operations SAS. So there is another one. It is more focused on ventilation control, high lift. So that will be, we try to have our first implementation of the ventilation control system in this architecture, DME. on the RCE, remote control electronics. So we intend to have our first implementation of the iLift function with common modular architecture again on the RCE, and to demonstrate the power management in interaction with ventilation and the iLift equipment. And also the electronic power control unit in an IMA and in a multi-system environment. And the interest is that those functions, so ventilation control system, so this one is IO intensive, and the iLift system is time critical, and well, the functional demonstration is to make sure that those type of applications can run at the same time and safely, and etc. And we'll have, at the same time, a functional demonstration of the power line communication. So that's just an example of another avionics function demonstrator that can make use of those new technologies. So this demonstrator is led by Airbus Germany. Another one is related to fuel. So we want to demonstrate fuel gauging using, for instance, powered by light probes, and demonstrate the fuel management using smart pump and smart valves, and using passive photonics pressure sensing. So of course we see that we use those new technologies, smart sensors, and we'll take benefits of the distributed modular electronic, the remote solutions, to demonstrate those aircraft functions, fuel gauging and management systems. So this is a third demonstrator that is led by Airbus UK in Filton. Another one related to landing gear. As you see, the idea is to assess electric braking on a distributed avionics architecture with a wheel remote data concentrator and with smart electromechanical actuator controller. And we also would like to demonstrate the capability to data load smart components. We'll assess at the same time, we'll evaluate optical sensor feasibility towards landing gear systems, and the secondary landing gear functions such as brake to vacate, runway excursion prevention. Those functions are already certified and operational. An example will be A380, and now we'll extend that function to other types, single wide and long range, of course. But the idea is to host secondary landing gear functions and to distribute them in this new architecture. So this is also a demonstrator that is led by Airbus UK. There is another one. The last demonstrator is led by Dassault Aviation, and the topic is open world, operator domain, and we are going to assess distributed modular electronics components in the open worlds. So you can see servers, NASM, SGM. I'm not familiar with the acronym, sorry. And we would like to assess the data exchanges between different functional domains. Functional domain, so the interconnection between the avionics world and the open world, having in mind all the time safety aspects and security aspects. We don't want to allow hijacker to interact with the aircraft, with the avionics, using failure in the design. So multi-host, multi-domain applications, evaluate communication nodes, demonstrate secured interaction between domains, demonstrate communication management capabilities. So I won't detail everything. So please feel free to ask questions to the people belonging to the consortium during the coffee break. So examples of functions, aircraft functions that will take benefit. And just to finish, we also have advanced studies at low technology readiness levels to progress towards new areas, to improve the developments of this IMA2G, and to ease the validation and the assessment of those new technologies. So we have various studies. I won't list them. They will be available in the presentation. But it's not just high-level technology readiness level. We have other studies, advanced studies in the project with many partners, universities, research centers. So that's the end That's the end of the presentation. That was just an overview for those who are not familiar with Ashley. Thank you.
No. So we start now the technical presentations, inviting, that starts with 3 Ashley universities. So I would call to the stage Arne Kruger from the Technical University of Braunschweig, right? So please.
Thank you for introduction. TVBS, that's it. Okay, as Teria has introduced, I'm a university partner of Ashley, and we are involved into navigation and air traffic management mostly. So, the institute I'm representing is Institute for Flight Guidance in the University of Braunschweig in Germany. I wanted to cover in my presentation very briefly. First, where we come from, introduce the concept of required navigation performance, which is a high-level concept that gives us the freedom to think on an academic levels about different ways to locate ourselves, our aircraft in 3D space, and give certain guarantees on how good we are at that. And I then go on to how we conventionally do achieve this goal, and then want to show what we're doing in Ashley, namely distributing all these mostly software functions amongst general computing modules, and what we think the advantages of such an approach are, and how we want to achieve that. I will talk very shortly about one more conventional approach, building upon what we already have in AFDX networks, and one what we would like to have, mostly involving a new middleware component that's not actually there. Then close with some open issues in the summary. This slide is meant to introduce where we are coming from. So we're mostly interested either in air traffic management on a high level. How good do we need to navigate to do our operational mission? And on another working group interested in how we do this locating ourselves. And the good thing is that the required navigation performance concept essentially leaves us a free way in using any sensor and any sensor source we have to achieve a certain goal. Conventionally, you would have had a single sensor dedicated for a certain flight phase. Say you have had your inertial sensors for over the ocean, you had certain radio navigational aids over land, and then you have got your instrument landing systems on approach. And then, of course, in the last years, certain other things popped up, namely space-based navigation systems, space-based navigation systems that were augmented from ground signals and all such things, and those opened up a lot of new possibilities to devise a certain position in space, that is, to navigate. And a conventional approach would not have allowed that, but with the required navigation performance approach or point of view, you could then choose, okay, I've got this and this and this sensor, and all together provide a certain performance that we can guarantee. And all these guarantees are, of course, figures, probability figures of some sort. And if you then build a system like that, that's actually a slide I picked from Anastasia EU project. It looks something like this. You've got an air data inertial reference unit containing certain sensors. Those sensors are the diamond shapes, together with some software components that are able to use these sensors to get some preliminary position. And then you've got receivers, multi-mode receivers, connecting to GPS and instrument landing systems. Those also have some software functions associated with them. Then you've got some radio navigational aids down there. And all these feed into what's commonly called a flight management system that then fuses all these data together and does some selection on what's actually the best solution and what provides which guarantees. And this slide is there not to show that it's all bad, because obviously it does work like this, and it does function. It's mostly there to show very briefly that a lot of this stuff is indeed software. All the green boxes are software functions, mostly. And then we've got a certain set of sensors which we don't expect to change. We expect that most of these sensors will be more or less the same, but how we interpret the signals of these sensors is in fact something that's very much in flow. A lot of research is going on how to use these sensor data mostly from, for example, different space-based navigation systems to fuse a more reliable position even in times of bad signals or error. So most of the things we do is software. For us, the sensors are more or less God-given, and we use these data to do our thing. And currently, we still, unfortunately, have a rather tight binding between the software functions and certain hardware components which we want or think we need to break up. Since my institute is mostly involved into fusing GPS or space-based systems with inertial sensors, I will now skip most of the other flight management functions for the remainder of the presentations. But of course, they are still there. It's just other people who are involved in it. Coming to these open issues that we think emerge from the traditional approach. We've got a lot of software, and we think that software is the thing that will change most rapidly over the lifetime of an aircraft. So we think that updates over the lifetime of the navigation software are common and are expected. Still, we have this tight coupling, which we want to break up, and which is, as we understand, basically what we are doing initially. Breaking up dependency between software and hardware, getting to a more manageable approach. And we want to get away with specialized hardware-software interaction, which leads us to something that I try to depict here, where we strip all these sensor stuff from specialized software functions, basically, making them kind of dumb again, but that's of course not a nice thing to say. Only leaving some pre-processing on all the sensor nodes, and then distributing all the small, all the different software functions amongst different general computing modules. And the point that we are pursuing is that what was before a more or less monolithic big chunk of navigation software is now split into many, many smaller parts that are hopefully more or less equal in size. So they are more easily distributed amongst whatever computing resources are there to spare. You don't need to dedicate a whole computing module just to navigation, but you put your smaller navigation functions to whatever computing modules you have. That is, you cut a big part of software into smaller parts that are more easily allocated and scheduled on your computing system. And what I've tried to depict here, and during our kickoff meeting, a bit misnomed as a database, is of course not a database in the classical sense, where things go in once and are then distributed many times, but it's more like a shared memory or some kind of scratch pad, which is synchronized and distributed amongst all these general computing systems, and which is the interface between the small software functions that as a whole comprise the navigation system. We hope that we can, by this, improve the utilization of computer resources on one side, get an abstraction from hardware, and also allow to mix and match these functions as we see fit. Of course, a big airliner will always use the full suite of sensors that is available. But if you're going down to smaller general aviation aircraft or special mission aircraft, you might find that you don't need all the sensors that are available, but you only integrate those software functions that you see fit, for a certain application. And that gets easier than beforehand. You have thought about how these individual software functions actually interact, and you have a framework in place that allows you to integrate those software functions in a more easy and manageable way. Our current status is that since we are a university, we are not doing industrial scale software development. We've got instead a certain set of certain code base available, developed both along the years and in many national and international projects. We call Tripos, which is currently comprised of a very customizable and configurable set of different navigation filters and sensor fusion functions, but is at the moment built like a monolithic single-threaded block meant to be executed on a single machine. And we are redoing or refactoring this code base to be distributed on multiple machines. For our purpose, it will be PC-based machines, which we nevertheless will fly in our research aircraft. So it's not going a desk solution only. It will fly, it did fly, but it's not going to be flight-qualified hardware in the sense that Airbus or Thales will accept, of course. And we want to, doing this, investigate all the issues that might arise. And one issue that will arise and is clearly on the table is how do you manage to integrate these small functions with each other. Of course, you have to somehow specify who talks to whom and how he does and what he talks. And what we have at our disposal now is basically these AFDX sampling and queuing ports. Of course, we could use those. That maps quite clearly to sockets on our PC hardware, and is in fact usable to integrate these smaller software functions. But it's a lot of hardware, a lot of management overhead to actually do this for each and every function and for each and every configuration. And we feel that that might indeed be a lot of effort, because we of course aim to get a very small granularity, a lot of small functions rather than few large blocks to get the most of the benefit. So we expect that this will create some scaling issues if we use these conventional dedicated links between functions that we then have to manage somehow. Instead, we would like to have some kind of middleware in between that, similar to other software packages, does some of these data distribution services for us, so that we can more easily develop the software in a manner that we are used to. That is, we are developing against some kind of virtual machine that then just happens to be distributed amongst multiple modules. At the moment, we are investigating what kind of available middleware components we can use to demonstrate or to investigate how this will work out. But of course, I hope that we can, in the coffee break or in the marketplace, ignite some discussion on whether that is indeed a feasible approach in an avionics domain, and what guarantees would be needed or can be expected from such a middleware. Of course, what we are doing here is we're picking a very specific software-centric function. But in general, every other function that has a lot of number crunching to do can, in fact, try benefit from these investigations we're seeing. So the open issues that are clearly there is what is the granularity of composition. Basically, we could take all these boxes from the presentation and keep it like this. But if you go a step further, you could also say, okay, we've got a Kalman filter there. It usually has two steps, one predictive and one correction. Why not cut it in half, have it one place there and the other step there? So you have a very small pieces which are more equal in size and that all more equal to be scheduled. But also everything comes as a price. It's nothing for free. So you also have to have the bandwidth for that. But it's not too much of a problem for us because most of our operations are not extremely time critical. So the time scale is not in the range of 5 milliseconds or something. It's more medium criticality. Still, the need, of course, to have the data in time and correct, so it's still an avionics application. And then, if you got so many micro partitions going on, how do you manage to reschedule in case of failure to a backup node? I learned that this has been covered in Scarlet. We've not been in Scarlet, so we don't know exactly what has been done. But maybe we can get into discussion on this topic too. Maybe this is a no-brainer and all the methods are in place, but maybe this does not scale well. And so we have to look into that again. It's basically me who does the technical work. My colleague Thomas Feuerle, who could not be here, is a contact for more organizational and possibly cooperational issues. So feel free to contact either of us or me in the coffee break. I hope we get some discussion, and I'm open to questions. Thank you very much.
This slide somehow illustrates the importance of dynamic program analysis in the life cycle of software. Programs contain defects, and then the developers usually employ some analysis tools to help identify these defects, and the analysis results afterwards used to fix the programs and to improve the code and so on. So dynamic analysis is widely used for debugging, like memory leak detection or data race detection, for performance analysis, various forms of polycontext profiling, block contention profiling, for example, also for testing, code coverage testing. So this is a really important tool practically, also for building embedded systems, of course. And if we focus on the Java platform, then there is a huge number of different tools aiming at supporting debugging tasks, testing tasks, and tuning. But these tools all are based on low-level abstractions. These are very complex tools. Developing such a tool from scratch is very hard, and maintaining and extending these tools is very difficult too. Moreover, many of these tools have some well-known limitations, such as limited code coverage. That means that the analysis doesn't represent the whole execution of the program, but only part of it. And these analysis results can be misleading, of course. Now, our idea is to propose an all-in-one dynamic analysis framework that can be used for any testing, debugging, tuning tasks, that provides high-level abstractions for implementing a wide number of tools from the literature, also specific to the needs in this project, with only a little number of code. We already have some example analysis running in our framework. For example, code coverage testing, a crash reproduction tool, memory leak detectors, data race detectors, calling context profiling, object lifetime profiling. Some of them are our own tools, some of them were recasted from the literature. We are focusing on instrumentation-based analysis. That means we insert extra code in programs that produce events that will be analyzed afterwards. So we identify interesting locations in the program where we capture some relevant state and we pass that on to analysis. Here the red code illustrates the inserted code by instrumentation. and then the analysis operates on these events. The events can carry some payload, such as, for example, object allocation would carry the type of the allocated object or the size of the allocated object. So we call the instrumentation here the event producer, and the analysis is the event consumer. There's a large number of tools for doing bytecode instrumentation for the Java platform. We can categorize them according to the expressiveness or flexibility and the ease of use for the programmer. For example, there's ASM, it's a very well-known bytecode engineering library. It is very expressive. You can specify any instrumentation with it, but it has a rather low-level programming model. It just reifies bytecodes, and the programmer has to know a lot about the bytecode format to work with this library. Another extreme would be AspectJ, which is very easy to use. It implements aspect-oriented programming model where relevant events can be specified in a declarative manner and the code to be executed when these events are captured. However, it's very restricted. The event model is hard-coded and very limited. Many analyses cannot be expressed with such a model. So for the bytecode instrumentation, we aim at something here on the right upper corner where we have a high-level programming model that is easy to use, at the same time high level of expressiveness. So in summary, we want a high-level programming model, we want expressiveness, we want also full coverage from the start of the VM until the termination of the VM, and we want to guarantee isolation. That is, we don't want any unwanted interference between the observed program and the analysis. Achieving one of these features is very easy. Many tools do that. Achieving two is already a little bit challenging, but going for all the 3 or 4 is actually a major challenge. And the first one to have all the 4 things in place. Our first approach that we are using still for specifying the events of interest for the analysis is called DSL. That stands for Domain-Specific Language for Instrumentation. It's an embedded DSL in Java. It's an abstraction of the ASM library augmented with some aspect-oriented features. So it can be seen as a AspectJ extension also for being able to specify any events of interest. So it has an open join point model. That means any event can be somehow captured. You can also call it, providing that it, as of what you can see, is what you instrument feature. So you don't operate on an API with the bytecodes, but you specify code that you want to be executed at certain locations, and you declaratively specify the locations where this code should be inserted. So you write in terms of code snippets here. There are some reduced guarantees that the inserted code cannot corrupt the base program execution. That's only true if we don't operate with full bytecode coverage. With full bytecode coverage, there are some limitations. So on the scales I showed before, DSL would be placed approximately here because we can express almost all analysis that can be coded with ASM, and the programming model is similar to AspectJ. And we also did an extensive study by recast with users and by recasting existing tools from the literature that show that we have a similar code compactness like AspectJ, and we can express any relevant analysis. Now, before I mentioned 4 important goals: high-level abstractions, expressiveness, coverage, and isolation. The first 3 can be met by DSL, the 4th one, unfortunately, not. The problem here is that the observed program and the analysis code execute in the same address space, in the same JVM. And now, if you have instrumentation with full coverage, that means also the standard Java class library will be instrumented, and the inserted code there will use the standard Java class library again. However, the Java class library is not reentrant. There is a fix for certain situations, but still the programming model here is error-prone. Another limitation here is that the analysis runs in the observed program regarding memory consumption or resource consumption in general. For some analysis, like object lifetime profiling, even simple applications would use live analysis state of tens of gigabytes and final analysis results in the order of terabytes. Clearly, this cannot be executed in an embedded system. So we propose a different model called the Shadow VM, where we have a separate process which can run on a server to asynchronously and remotely execute the analysis code. That means the events will be marshaled in the observed VM and will be transmitted afterwards to the analysis VM. Moreover, we propose a Shadow VM programming model for making it more easy for the programmer to attach and detach shadow state to objects. This is something that's very common when you write your own analysis. To illustrate this, here we have the event producer, which we call the observed VM. And then we have the Shadow VM running on a server that consumes the events and builds up the profile. The communication is done by a socket. There's a native agent running in the VM of the event producer. And Java native method invocations are used for marshalling the events. The red code here is still instrumented code that is inserted, but it is constrained to be allowed only to make GNI calls to marshal events, so it cannot interfere with the non-reentrant Java class library. So the isolation problem here is solved. This shows the software architecture in a bit more detail. We have both an instrumentation server and an analysis server. They could be the same, but conceptually they are different. Whenever a class is loaded, starting from object, the root of the class hierarchy, the bytecode is first transmitted to the instrumentation server, where it is instrumented according to some user-defined instrumentations that are deployed there. And then in the observed process, you have only instrumented code running. The application code, as well as the class library, are all instrumented. And whenever an event is produced through the event API, it's transmitted to the analysis process, where we have an implementation of the Shadow API, and we have the user-supplied code that uses the Shadow API to perform the analysis. Now, this architecture allows us to attach multiple different processes to the same instrumentation server and to the same analysis server. And in the past, we only supported the Java virtual machine. And now, thanks to the work we've done in the last year, we also support Android here for embedded systems. Now, there are different types of events that we can actually intercept. There's a library of events that are very commonly used in many analysis tasks. You can specify user-defined events by using the Diesel language. And then there are lifecycle events that are created by the platform, which are mostly about the allocation and deallocation of resources. In particular, the deallocation events are very important. In the Shadow VM analysis side, we want to be informed typically when an object gets reclaimed, because if you attach some state with it, you can also probably get rid of the shadow object and compact the analysis state somehow. Otherwise, it's very easy to run out of memory, even if you have hundreds of gigabytes of data, of memory on the Shadow VM side for certain analysis. We support different event ordering semantics. Depending on the analysis, there are different requirements on the ordering semantics, and the programmer can specify that. There is the global order, in which case a single queue is maintained, and the events are all put into this queue in a synchronized manner, which preserves a large part of the happens before relationship in the observed program. And then there's the per thread program order, where each thread has its own queue, and now event production can be done without the need of any synchronization. So this is a trade-off between the guarantees which part of the happens before relationship is preserved and how costly it is to create the events. And the analysis can specify which semantics it requires. Then there are also customized ordering semantics that are, however, not so important. So assume you have an event here in the observed VM that as a payload has an object, a class instance, and a primitive int. Then this event will be reified on the consumer side as carrying a shadow object, a shadow class instance, and an int. And there's an API on the class hierarchy that represents this model. So every object becomes a shadow object, and There are specific subclasses for class and for thread and for string. For example, for class, the subclass is important because it gives you access to reflective information about the class hierarchy in the observed program. And very important here are the get state and set state primitives, which allow you very easily to attach and detach shadow state to objects. Very important is also that the identity of objects is preserved. That is, if an object is in the payload of multiple events, then it will be represented by the same shadow object instance on the shadow VM side. This is an important property for many analyses. Now, this figure just illustrates that when writing your analysis code, you can very easily attach and detach some shadow state there. Assume your event producers are Java virtual machines or Android VMs. Then the shadow VM will perform the analysis. And we introduced also a concept called shadow space so that multiple observed processes can connect to the same shadow VM instance and can somehow create analysis for distributed systems. If you think here of a distributed system that might have an enterprise server on the server side and an Android client, then you could analyze the whole distributed system with a single analysis. There's a specific features in Android that requires us to replicate shadow spaces, and this is because Android uses a special Zygote process that has pre-initialized state. When creating a new application, it forks the Zygote and the data gets replicated using the copy and write optimization of the OS. But this also means that there is possibly relevant analysis data in the Zygote that we need to replicate, so we had introduce a special lifecycle event here to deal with this replication. Now, the really good thing is that you write one analysis and you can analyze systems that run on a standard JVM and on the Android Dalvik VM. However, there are slight differences in the bytecode format. Like the JVM is a stack machine, the Dalvik VM is a register machine, and some translation of bytecode is performed. And this can create a bias in a certain cases of profiles. This bias could be corrected, possibly, but we haven't yet done that. Another big issue is that in contrast to the JVM, which has a JVM tool interface, the Dalvik VM doesn't have such an interface. So there's no Dalvik VM tool interface. This interface was essential for us to get information about object deallocation. Now we had to do that ourselves on the Dalvik VM, and we had to modify the Dalvik VM, and this means there's always some effort needed if we move to the next version of Android. So these are clearly some limitations. We already have some working tools, like a calling context profiler, various code coverage testing tools, object lifetime analysis tool, some tool for checking field immutability, and we are working on many others at the moment. These publications here summarize my presentation, give a bit more detail about the technical aspects. I would highlight here only the last one, because that's the part that we achieved in this project in the last months. So I will stop here, and I'm ready to take your questions.
Thank you, Walter.
Thank you.
Already start. So my name is Stephen Dominiak, also from Lucerne, a short drive to the Gotthard Tunnel from the previous University of Lugano. And I'll be talking today about model-based design in the development of a power line communications physical layer. So those of you who aren't involved in the design of communication systems, which is probably many of you, basically there's this OSI model which divides a communication system up into different layers. So the physical layer is the lowest layer, which is responsible for the transmission and reception of physical waveforms. But first I'd like to go back and define what power line communications is, just so it's clear. So typically, or almost always currently, avionics systems have a data network in parallel with a power network. So the data network provides the information between distributed elements. The power network distributes the power that's needed to power the devices. With power line communications, we completely remove the data network. So basically now we have a single connector for power and data. One part of this technology is that the data transmission is also independent of the underlying power signal. So it really doesn't matter too much whether it's DC, AC, or the voltage level, with some small exceptions in terms of the analog components. What are the advantages that power line communications provides? Well, as we show, it's obviously the reduced wiring weight, volume, and complexity. One other thing we can get from the technology is also typically higher data rates than traditional avionics data buses. That doesn't mean that we're trying to achieve here several megabits. What that means is that we have more capacity in our channel, that we could use that available bandwidth maybe to increase our reliability, which is a target for avionics systems. What is the main challenge of using PLC? Well, in order that we provide robust data transmission over our unreliable medium, so the power line or the power distribution network has not been designed for high-speed data transmission, we need increased complexity in our digital signal processing. So that's what I'll be talking about today. But first, what are some of the characteristics of the transmission of a PLC signal? Well, let's first look at the channel. Here we have some channel measurements that were actually done on a wiring harness from the cabin lighting system of the A380. So what do we see? This basically shows the attenuation on the y-axis and the frequency on the x-axis. So what we could see is that the channel changes versus frequency. We have these notches that appear all the time. So those are frequencies where we have a high level of attenuation, much higher than other frequencies where we have a low level of attenuation. We also see that the channel varies. So these are different points on the harness. So we see that the channel varies from one location to another. So that's the channel and the attenuation that we have to deal with. Then there's also noise. So the noise conditions on the power line are a lot different than the noise conditions on some kind of data cabling. So we have to deal with transient and impulsive noises that are generated. We also have to consider the EMC limits. So the easiest way to improve performance would be to increase the transmission power that we use. But the DO-160 tells us, no, we can't do that. So basically, DO-160 is a relevant EMC standard which limits the amount of high-frequency noise that devices could produce on the wiring or the cabling. We need to adhere to these limits as well. But here we see an actual measurement that was done in a previous EU project, TAUP. So it was, we did the radiated and conducted emissions measurement, and we kind of showed in a first initial feasibility that yes, we can do power line communications, and yes, we can adhere to those limits. So of course, this will be another topic that's being investigated further. So this, all in all, this means that our PLC physical layer has to provide robust communications in low signal-to-noise ratio conditions. So that's basically a ratio between what our received signal level is and what the noise floor is. So we need to work when we have low SNR. We need to cope with this frequency-selective channel, and we have to somehow mitigate these short-term noise transients. So without going into the theoretical background of digital signal processing, just to show some highlights about the techniques that are used with PLC. Well, first of all, we have forward error correction, where we add redundant bits in order to be able to correct some errors at the receiver. So this helps with things like the impulsive noise. We use orthogonal frequency division multiplexing, OFDM, which is actually a technology also used in the new 4G LTE standard, where we take the serial stream of bits and map that in parallel across the frequency axis. So this helps us to cope with these notches that we saw before. We do things like scrambling and interleaving, where we do bit reordering in order to guard against burst errors, so that burst errors affect as few bits as possible. And then we need to do channel estimation and synchronization to cope with the fact that our channel is actually different from one point to the other. Just to show you a little bit what that means, here on the left we see it's taken from an Ethernet signal. And here it's kind of clearly visible, if you've ever worked with communications, where bits are and how those bits look. On the right we see a PLC signal, which looks more like noise. So this basically comes from that OFDM. It's the sum of all of these bits mapped across the frequency. What our digital signal processing allows us to do, there's information in this signal, and it allows us to extract that information even in a robust manner, even when we have these adverse signal or adverse channel conditions. We're responsible in the Ashley project for providing a PLC prototype. So we're going to demonstrate the functionality of PLC, and it's going to be a solution which is dedicated for avionics applications. Our target platform for this resource is the Xilinx Zinc system-on-chip platform. So we'll be realizing actually the physical layer part in the FPGA part of that system-on-chip. The challenges for us is that we are using, or our solution is based on an international PLC standard, but many aspects of that standard are left open for proprietary implementation. So that means we do have significant design effort. So basically the standard defines the transmitter, but not necessarily the receiver, how you implement that. We're also optimizing our protocol towards robustness, low latency, and determinism. We're realizing that protocol on an embedded target platform with all the constraints that come from that. And we're also considering implementation safety aspects from the very beginning. So those are the considerations for the relevant design assurance guidelines, which basically tell us there's one standard for hardware and one for software, which tell us objectives that we should be achieving in order to ensure we haven't introduced additional errors into our implementation. And for this, we've introduced the concept in our process called model-based design to cope with this inherent complexity. So if we look at model-based design, what does that mean? Well, a model is an abstract representation of a system used to support the development and verification process. Model-based design is becoming more popular now within the avionics industry. And even so that in the newest version of the DO-178, which is the design assurance guideline for software, so the newest version C, there's now a supplement which has specifically addressed model-based design called DO-331. And within DO-331, we see different use cases for using model-based design. So first of all, to provide unambiguous expression of requirements in architecture. So here we see basically that a model can directly express requirements and/or architecture. Support the use of automated code generation. Support the use of automated test generation. Support the use of analysis tools for verification of requirements and architecture, as well as supporting the use of simulation for partial verification of requirements, architecture, and/or executable object code. So partial is important. Hardware testing, they still define as necessary, but you could partially verify your requirements. Here we see executable object code. As I mentioned, our physical layer is actually VHDL, FPGA, but the relevant design assurance guideline for hardware, DO-254, doesn't address model-based design. That's why we're now applying concepts from DO-331 actually to our hardware development. So, with these design assurance guidelines, or generally design of avionics systems, there's typically two levels of design, or two levels of requirements, if you will. The high-level design and the low-level design. We're actually using model-based design on both levels. So first of all, the high-level design, DO-331, calls them specification models. They basically represent the high-level functionality of the system. And we have developed those models within MathWorks Simulink. So our models consist of a mixture of MATLAB code, Simulink blocks, and we have also partially C code in there in order to speed up our simulation time. So here we have kind of high-level abstract functions representing the different blocks and functionality of our PLC transceiver. The model-based design aspects that we use here from that previous slide are an unambiguous expression of high-level requirements and architecture, as well as using simulation for partial verification of requirements and architecture. But then also for our low-level design, and if you look at kind of a definition for those of you not familiar of a low-level requirement, it should be a requirement that's specified well enough that you could actually develop code from that without any further information. So So that kind of gives you an idea about the scope that you need for low-level requirements. So our low-level design is also captured in models. And here we use Xilinx System Generator. So System Generator is a tool provided by Xilinx where you can do DSP design using graphical blocks. And it allows you to do bit and cycle accurate simulation of your DSP design. And it's actually a plugin or a block set library provided within MathWorks Simulink. So the model-based design aspects we look at here. Now we have the unambiguous expression of our low-level requirements in architecture. Here we use currently automated code generation. So actually from our system generator design, we generate the VHDL code, which is then put into the FPGA. And we use analysis and simulation for partial verification of requirements in architecture. So that's talking about going down the design path. If we look now at the verification, so we first, in an initial step, do a high-level design verification. Typically, we're verifying this through looking at bit error rate curves. Not exclusively, we also do functional testing, but in terms of performance, we're looking at bit error rate curves. So we perform simulations under various PLC channel conditions, which is the benefit of a simulator. We can reproduce those conditions, including worst-case conditions, or what we expect as worst-case conditions. In these simulations, we can investigate if the results correspond with the theory. Do we get our expected results? How do optimizations we do influence the performance, either positively or negatively? And which optimizations provide the most robust solution? Because that's what we want for an avionics data bus, robust communications. So here, just to show you a comparison of PLC against standard data networks. So on the x-axis, we have signal-to-noise ratio, which is a common metric for measuring communication systems. And on the y-axis, we have bit error rate. So basically, for a given signal-to-noise ratio, we want to have as low a bit rate as possible. Or in other words, these curves should be as far to the left as possible. The red curve here shows the theoretical bit error rate curve for the modulation used in 100 megabit Ethernet. The blue curve shows the curve for CAN, assuming we have 1 megabit data transmission. And what we see now, and maybe to mention, both of these curves have been simulated with a channel which is typical of a data network, something called an additive white Gaussian noise channel, so fairly good channel. Now we have two curves coming from PLC, one here in the middle with the modulation achieving 40 megabits per second, one here to the left with the modulation achieving 20 megabits per second. Both of these curves have been simulated with a power line channel, so a channel with plenty of those notches and also impulsive noise. So we see that with PLC, and this is just the standardized solution, the solution defined in the standard, we still achieve fairly high data rates, 20 and 40 megabits per second, on an adverse channel, while still providing a solution which is more robust compared to these standard data protocols. And now one thing we're doing is looking at optimizations that could be done to shift these curves then further to the left, because we have plenty of bandwidth. 20 megabits per second is typically a lot more than we need. So we will be using this bandwidth then to optimize our robustness, reduce our latency. So that's high-level design verification. Then we go down and do low-level design verification. And here we've developed a platform within Simulink, which allows us basically on a component or module level to basically run a simulation, decide whether we want to simulate with a specification model or a design model. So we could have different inputs, select whether we're simulating the specification model, the design model, and then directly compare the outputs in order to verify that the behavior of our low-level design is the same as what we've developed in our high-level design. Then further, so that basically has tested and verified a design, but further we want to go forward and do hardware testing. So make sure that the automatically generated VHDL code has the same behavior as what we've simulated in our model. So we've also extended this platform to do testing on our hardware. So basically we have kind of a software-controlled testing in which we verify that at a module level that the inputs and outputs from these different components are also the same actually in the hardware realization. So we verify the automatically generated VHDL code as well as the synthesized netlist of these modules. One last thing to mention, basically where we have a low TRL technology here, PLC, so we have an R&D type of development here. And due to this, it necessitates an iterative approach. We're not going to get it right on the first try. We see that hardware constraints is an example of things where we struggle a little bit with. Hardware constraints sometimes lead to reduced performance. So we're realizing this on an embedded platform. We need to know that we can't use complex mathematical functions, but we have to use approximations here. We have the typical problem, floating point versus fixed point arithmetic. We also have resource limitations. If we're using tables, we can't make those tables arbitrarily large. But model-based design allows us to simulate and investigate the influence of these constraints already in an early stage. Other things we've done in order that we could have quick turnaround time when problems are identified. I mean, the goal is to identify them with this V model as close to the top as possible. But we have established traceability, so we could see even if we're further down, if we have a problem, what the impact of that could be. And we've also automated the execution of our test cases. So that's nice. If we have some kind of change, we don't need to manually execute or re-execute all of these tests, but we could do it automatically. So in summary, the University of Lucerne is providing a functional prototype for the Ashley project, and it's actually going to be in the high-lift demonstrator, as we've seen before. We've used model-based design for the development of the physical layer in order to cope with the complexity of the necessary digital signal processing and ensure that the low-level design as well as the realization is conformed to the high-level design. And maybe just to briefly show you, some of you may be familiar with PLC from the electronics store where you can get these wall plug modems, so the consumer technology. Basically, the consumer technology optimizes, they want to provide you as much throughput as possible. They want to have 500 megabits on the packaging. But you can't, I mean, we have throughput, latency, reliability. You can't optimize all three at the same time. So they optimize throughput at the cost of higher latency, lower reliability. Now, what we're going and doing with our avionics PLC is optimizing reliability, achieving our necessary latency requirements, but that's going to be at the cost of throughput. So we're not going to be showing anything like 20 megabits per second. Our goal is to achieve the reliability and provide a deterministic latency. Okay, thank you.
Okay, so the title of this talk is Agile Methods Adapted to Development and Certification of Avionics Software Systems. And it's related to task 4502. And as you see, we have just started month 10, so I don't have a lot of results, but I will talk about the ambition and how we are planning to do the work and hopefully convince you that this is a relevant type of study, although it's kind of different from the other studies as far as I see. So just a few words about SINTEF. It's a large research institution in Norway. We work on many topics, but my background is in software development and software process improvement. So that's the type of ideas I'm bringing into the project. And then we have the other main partner for this task is NRR. And as you know, they work a lot in avionics. They do a lot of software development, and they know the standards. And the 178 standard is kind of important to this task. I'll come back to that. So they have a lot of knowledge and experience to contribute for this work going on. And as you see, they have many years of experience in these types of projects. Scarlett, for instance. Okay, I have put in the words defining the work we are doing from the description of work. And what we are supposed to do is to recommend a tailored software development process for the ASHLI consortium. So we plan to provide some, maybe not a complete software development methodology, but some good guidelines and tips on how software can be developed differently from you do today. We are using this opportunity to think about the idea, how can we improve software development? Because it's a huge cost in these projects. So we will work with some of the partners to learn more about the needs and constraints regarding software development and the performance of doing that. And we will provide some guidelines by the, I don't know, end of next year or after summer, I think. And we will also turn to the research literature to see what are other actors that develop safety-critical systems doing with respect to software process improvement. So SINTEF and NLR are sort of leading the work, and we have some industry partners with us, Celex and Nordmicro, and I have been approached by several other companies during these 2 days that show interest in this study, and I suppose we will work with more partners, especially after the new year. So the background and the motivation for this work is, of course, as you know, that developing the software for these types of systems is very complex, it's very costly, it's a challenging type of task. And my claim is that we see a trend that more and more of the total development of avionic systems moves from hardware to software development. At least that's a trend we see in other high-integrity system domains. And it's also an increasing demand for higher safety integrity levels or safety performance in these systems. And the way we tackle this complexity is by adding formalism in methods and ways of working. However, we could claim that formalism increases costs and it reduces flexibility. And we would like to see costs reduced and flexibility increased. And that's sort of the goal for the work we are doing now. And also, these are systems that has to undergo strict certification, and that's it's a very high cost to provide the documentation needed to prove conformance to mandatory standards. So the research question, and this is a very research-oriented type of study, is can principles from agile software development mitigate some of the challenges of development and certification of airborne software? We will pay particular attention to the 178 standard because the guidelines we plan to propose needs to match the standard. We cannot compromise the ability to perform according to the standard. That's kind of it's a really important challenge for this study. And we are looking at revision C because we had some discussions yesterday about B or C. So we are looking at C. And just a reminder about the levels of severity. And I think some of the systems that are being developed or trialed in this project are very high on this list, like fuel systems, landing gear systems. They are quite high, meaning that the standard will impose more requirements on how software is being developed. And we need to think more carefully about guidelines for developing software. Okay? I see from my few months working in this project that the V model is kind of the standard way of thinking and working. And if you allow me to be critical, I know this has worked for many years, but we could claim at least that this way of working sequentially, starting with a lot of planning and early on, it gives us low flexibility when it comes to working with requirements. And what I see from software development projects, requirements tends to change as software grows. So I would say that there's a need of tackling requirements managed during development better. And this model, at least conceptually, it's not good for tackling flexibility. And of course, if we see that we discover problems, critical problems late in the development lifetime, the cost increases to tackle the problems. So the idea is to discover problems as early as possible. And that's kind of one of the ideas of agile methods. I will say a few words about that in the next slides. And also part of this process is that it's kind of costly to produce certification evidence by producing a lot of documentation. So part of the goal is to reduce the effort and the costs of producing documentation. And also we would like to improve time to market performance. So a few words about agile software development. I suppose most of you have heard about the term. It's a way of organizing software development, which has been around for, I would say, 15 years now. It has become more or less the standard for the non-safety critical software domain. It hasn't had an uptake in the safety critical software domain, like avionics, but there is a lot of interest in the industry. I will show you some examples later on. There's a lot of text in this slide, but on the bottom you see the key components of agile methods like Scrum or XP. You might have heard those names. So the idea is to work in an iterative fashion, building the product piece by piece, being able to demonstrate how the product works when it is developed. Also, it's an incremental type of process. It's a type of process that provides a lot of feedback to the development team and to the different stakeholders. So the idea is to constantly have a good overview about the status of development and also problems that arise, to be able to deal with them as early as possible. So continuous integration, continuous testing is part of the idea. This enables, we see at least in some cases, a more flexible way of managing requirements. And part of the idea is to have self-managed teams and a close participation from the customer or the ones that own the system being developed. So we have had one meeting now in just a few weeks ago in the Netherlands, starting with the mandate from the description of work, and we thought about how should we approach this task, because we have a relatively short work period. We are supposed to be finished in month 23 of the project, so we have more or less a year left. What we see is that we need some input to this study, this advanced study. And the first type of input will be to go to the research community to look for scientific publications, to see what other people in other domains have learned so far about these issues. And we would like to do that and compile an overview, which I think could be of interest to the Ashley Consortium. And then we need to speak with the partners. What are their needs for improving the software process? Because we say that we will provide some guidelines, but they should, of course, be based on needs for improvement. And because the standard is so fundamental, we will do an analysis of the standard. Because, as I said, our guidelines must be aligned with the standard. So we need to know that they match. A mismatch would be bad. And then, in some format, we don't know yet, we will provide some guidelines that could be used by the partners, either in the Ashley project or later on in other projects. And because of this, the limits of this task, we don't have time for industrial trial. You know, ideally, we would like to provide the guidelines, have someone to try them out in a real context to evaluate the effect of them. We don't have the luxury or the time of doing that for this task. So I see that, for example, we will have a workshop in August next year where we present our results and we get some feedback. So it's kind of a subjective evaluation. I think that's kind of the maximum we can do within the limits of this work. So the status, as for now, is that we are in the process of reviewing the state of research. We have identified some relevant studies. We are putting them together, so I think we will provide you some type of white paper during the spring, giving you a good overview of the research within this field. And we have detailed the work plan. And just to take a step back, the strategy for this work will be to collect input from three sides. We will talk to the partners. We have identified a few to know about their improvement needs based on their experience in this domain. So in practical terms, I see we could have a workshop, let's say in February, with a few partners, where we collect these needs and needs for improvement of the software development process. We are also discussing the idea of issuing a survey within the whole consortium. And to me, as a researcher, it would be really nice to get an overview about the status in the avionics domain. So there are some actions coming up on collecting improvement needs. Very important. And as I mentioned, we will turn to the body of knowledge, research literature. What do we know so far? What are the results? What are the constraints? What are the good ideas? What are the bad ideas? And we will look at the standard. And having these three inputs, we will somehow shape some guidelines for how to do efficient software development of this type of systems. So, I see I have the old version of the presentation somehow. Let me switch to the most recent one. I put together this list. It's not meaning that you should memorize all these titles, but just as a taste of what we have found so far. So my message by showing you this slide is that there's a lot of literature, quite recent literature out there. It's very, very interesting, very relevant. I even found some papers issued by Thales. So you have people in Thales working on these issues, actually. And there are some workshop papers, but also some scientific journal papers indicating a high level of quality of these studies. So, and I suppose maybe the number of studies going into our work will be the double. So we will see a list twice as large in the end. Renee sent me this picture just for fun, and it's late in the workday. And my message by showing you this cartoon titled Cat and Dog is that when I talk about applying agile methods in this domain, I know that some sense that it's kind of too radical for this domain. And people are used to their old ways of working, and they do work well. But I see this as an opportunity to maybe think some new thoughts, have some new ideas. And I see that agile methods actually perform quite good in other domains. So I'm curious, could we see the same benefits in this domain? I think so, and we will work out on those questions during next year. And if you have questions or comments or ideas, we are really happy to hear from you. And actually, this is my last slide, so I might have saved you some time. And I'm open to questions or comments now or later.
Moving from tools to components, IAMA components, right? Martin Eil from Hamburg University, Technical University.
Okay, so also welcome from my side. My name is Martin Halle. I'm from the Hamburg University of Technology, so I'm one of the university partners in the ASHLE project, and I'm talking about configuration management for next IMA generation. I think Pedro Costa has made a very good introduction to it already, so it is similar to that, and I'm also going to go into more detail with respect to the ASHLE tool framework, so I think it is a very good continuation of that presentation. Okay, good. We have to show a preface. With respect to the content, I'm first also going to introduce our university, our department where we are working on, what are the typical topics for us. Then I'm going to address specific research topics at our institute with respect to IMA. And then I'm going to talk about the configuration management and two specific aspects we are focusing on in ASHLE. Just two are highlighted here. And then I'll come to the conclusions. So first of all, where are we? The Hamburg University is actually situated in Hamburg-Harburg, which belongs to Hamburg, but is outside city center, I would say. However, there is the Department of Aircraft Systems Engineering, which belongs to this university, and this is situated in Hamburg-Finkenwerder, so just besides Airbus, and we in fact share a building with Airbus. It was funded, or it was created due to a public-private partnership years back. And we have 27 research engineers, head of our department, of course, and some technical people. We have different research areas, in fact, so like hydraulic systems. So, of course, everything is somehow focused on aircraft systems. So we are addressing hydraulics, electrics, cooling systems, avionics, of course. We have a big facility for large test benches. So our typical domain is that we have industrial projects with an industrial partner focusing on one technology, which we bring into a test bench to really validate it and to make it ready for an industrialization. We don't do an industrialization, we can't do this, but we prepare it for it. With respect to IMA, we have actually three main domains where we are working on. First domain is IMA architectures and modeling and optimization of IMA architecture. So this is more in the very beginning. If you have no clear understanding about your modules you are going to use at IMA, if you have no clear understanding about I/O, for example, and about the resources you need. The goal of this is actually, the long-term goal is that you could create an architecture by using models. Second point or bullet is IMA concurrent configuration in engineering, which could be seen as an enabler for auto configuration in a long-term future. Here the task is actually to somehow handle the complex configuration domain within an aircraft industry where there are several partners, module suppliers, function suppliers, system designers, and so on, and they all have to share information to actually implement functions on IMA hardware. And this is an iterative process, so in the beginning you don't even have concrete modules, you don't have any concrete hardware, but you start already thinking about functions on running on hardware not yet present. And the last part, more or less the smallest part from our department, is IMA component modeling and simulation. For IMA platform simulation on a very abstract level. So we are not focusing on very deep down, but we want to use this, for example, to evaluate specific figures for EMA architectures on a higher level approach. Okay, what is the goal for us within ASHLAE? We take part to harmonize the IMA development process, focusing on what we have heard already, maybe not, on the seamless tool chain. So we have several tools in the IMA project which we try to harmonize using the ASHLAE tool framework already mentioned. We develop and enhance interfaces between the tools we are going to use. And in the end, we also support the process for the demonstrator. What I've shown here in the pictures actually several tools which are going to be interconnected within the ASHLAE tool framework. They all have different tasks to do, and they all have usually also different users which have a specific focus on the IMA domain. For example, functional modeling, platform evaluation, platform configuration, of course, platform optimization, verification, and so on. You can see it on a picture. And the arrows between those tools are actually the interfaces we are trying to harmonize within the ASHLAE project. What I would like to highlight as one example is the interface between the platform optimization and platform configuration tool, and I'm trying to explain what the actual issue is here and what the benefit would be if this would be possible. So I'm first going to talk about architectural optimization. What is the actual task here? The scope is also model-based design. So we have developed a meta model for avionic architectures, generic avionic architectures, so no specific ones. We can model requirements on the architectures, like requirements with respect to memory, for example, with respect to I/O, to resources in general. You can use such to do major design verification of your overall system at aircraft level, so taking into account not only one single system, but several systems together. And you could evaluate some design parameters like mass, for example, very early in your process. Using this methodology, it is also possible to optimize such architectures, as shown on the right-hand side here. So you have we have implemented, based on this model, which is very simple, shown here. I've forgotten to mention this. We have implemented some optimization routines which allow you to optimize specific design tasks. You have 3 levels of optimization. The first level is corresponds to an assignment. So, for example, you want to assign devices to a specific location in the aircraft in an optimal way. For example, to reduce cable lengths. You want to assign functions to modules. You want to, well, for example, assign links and so on. So these are, let me say, the easiest assignments. Using these, you can come to so-called multi-objective optimization, which means that in a second level, you could try to optimize the device types. So that you say, okay, if I would have a device type with a specific resources or with a specific amount of I/O, I would end up with an optimal number of devices at aircraft level. Or questions like, what type of devices are optimal to be distributed in an aircraft so that they have less weight, for example. And the third level of automation is actually the topology optimization, where you basically don't specify very strict constraints, but you leave the optimization completely to the tool. Of course, this takes large amount of time, but it also increases the optimal solution or the optimal architecture solution you can get in the end. So this is with respect to optimization. I will come now to the other end. So optimization is in the very beginning. You try to find an architecture to optimize it. Once you have defined architecture, once you have defined modules and so on, you're starting to integrate functions, and then you end up at the other end with the configuration management. So here we have two different scopes. First of all, is of course the configuration data itself. So we have developed a framework for so-called concurrent configuration in engineering, which implements the concept of so-called virtual module. So you can configure several types of different modules, which you have in an aircraft nowadays. And it allows you also for early validation of your configuration, because errors in the configuration are critical. If you realize them very late in the process, in the integration part, it becomes costly in the end. Second scope is the configuration process. So we try to implement, or we try to harmonize a massively, let's say, parallel and distributed development process. I've shown on the picture below here that you have several actors who are responsible for different parts in your module, and basically you have in parallel working hardware development, software development, of course taking into account design measures and so on. So the focus here is that this is computer assisted, especially with respect to validation. So I would like to highlight now one aspect, what we try to develop within the Esche project with respect to interfacing. So what we want to do is that we want to actually combine, on the one hand, the very abstract model you get from the optimizer tool, from the architecture tool, with, on the other hand, the very low-level tool you have for the actual configuration for dedicated modules. So for the optimization, you have usually very abstract modules, and you don't even know how they are called, probably with abstract links, abstract routing, abstract resources, amount of resources. On the other hand, you have these very specific modules, like a CPM and RDC, whatever you're going to develop. You need specific I/O channels, clarified, specified, AFDX, CAN, whatever. And you have also detailed routing parameters, because you know exactly where your modules are, and so you know how you have to route the information with respect to configuration. So the target within Esche is to interface both tools so that you get what I call blueprint retrieval of a configuration coming from an abstract world to deliver to a very concrete world. So that you can auto-generate the high-level global configuration for your architecture, so for the overall aircraft, in fact. And what we want to use here is the model-to-model transformation, because both tools use meta models, so there is the opportunity to use modern model-to-model transformation techniques to transfer this information from one domain into the other and then just reuse it there. The benefit would be that you have an error-free transition of information. You have very specific, very special parameters for every domain, but you, through the transformation, you ensure that you really take the information you need from the architecture model into the concrete configuration in the right way. So that would be the benefit. Another aspect I would like to highlight, so we are now aspect validation, we are leaving the interfacing, is the configuration itself. So as I mentioned already, we have developed an integrated framework which is based on the Eclipse framework for configuration management. The general architecture is shown here on the right picture. So the data model itself with respect to the parameters, and these are many configuration parameters you have to manage, several thousands, is defined in terms of meta modeling. The software allows you to create, validate, manage in general those configuration parameters at aircraft level, so meaning taking several systems into account at module level, where just some systems may run, partition level and network level in the end. And it allows you also to do some typical project management for different aircraft programs to compare or reuse existing information to cope with different users in the process, with different rights you have according to this, and also version control for the development process itself. So, one of the plugins, as I mentioned, the software is plugin based. So one of the plugins is the so-called Rule Manager plugin. It shall ensure consistent configuration data. So by validating configuration quite early in a process and regularly on the fly, so to say. It is dedicated to validate against so-called usage domain rules. These have several sources. They come actually from the module supplier. They have specific rules with respect to a specific module that need to be applied so that the configuration is valid and is consistent. There are design constraint rules which apply. One simple example are naming rules, for example. And there are also validation verification rules, airframer rules, and so on. So if different sources of rules that shall be applied and validated against your configuration data. You have different types of validation. So you can think of very simple, what I call an atomic validation. So you just check is the parameter present or not, is it needed or not. You can have more complex, like syntax range or consistency rules. And of course, most rules take several parameters into account and check several parameters against several other parameters so that a parameter set becomes consistent in total. What is also complicated is that rules may change with time. So you need to account for update of rules. You need to account for addition of new rules and so on, and observe the existing rules. So what we have developed is that actually those rules are not implemented, not hard-coded into the software, but we have several rule drivers, let me say, that allow to configure your rules. So all these different types I've just mentioned, you can specify with respect to XML definition files. So there you say name of the rule, what shall be evaluated, what parameters are used to evaluate an expression to obtain a valid configuration. Those rules can be versioned, so new rules or write old ones, and so on. And what happens is that in the software, the rule engine at runtime reads a set of rules, which can be different between editions of your software, and just evaluates them step by step and provides you with a reporting pointing to the actual parameters that are not consistent or that have errors or that are missing, for example. Those reports can later on be, so these are interactive reports, so you can click on it and then just come into the configuration tree to the parameter which you need to change or to adapt. Okay, this more or less ends my presentation. Maybe to summarize again what I've mentioned. First of all, I've introduced our institute at the university, at Hamburg University of Technology. One of our goals is to support IMA development through tooling. I've talked about optimization and configuration of IMA modules, what are specific research topics for us. I've talked about our contribution within ASHLE, so to support standardization, harmonization for the tool framework. And I've given 2 examples with respect to interfacing between tools and with respect to validation of configuration data. And this concludes my presentation. I'm happy to answer questions.
Thank you, Martin. Is there any questions?
here. I was triggered by this validation process of this configuration. It can be a huge number, and you talked about, in fact, consistency and that they are indeed that they are correct, that they are valid. And I was wondering if you use some kind of these rules, especially that these rules that actually check whether the configurations are valid or not, might be supplied by either the user or some other components of the system, and one can combine different rules. And then somehow, then the question is whether this combination of rules is in fact vacuous, whether it is consistent, whether it will indeed lead to the result that you expect, that is somehow it will not have false or positive or false negatives. I mean, is there work in this sense, or is it based on the experience of the...
Right. Okay, so first I have to mention, which is maybe not clear, of course, in the final product of an aircraft, we have specific modules. Those modules come with a qualified tool chain which ensures that the configuration is consistent. This tool chain is supplied by the module supplier, and this is a software which needs to be qualified. Right. So what we are focusing here is during the development, it helps you to early validate against these rules in a non-qualifiable way. Right. So it is just to help you in development. The idea behind is that you can easily add rules or add validation rules and compute them, but of course you are responsible in this particular software to ensure that the overall rule set is consistent in itself. So of course you can imagine that you can implement two rules that are misleading. The one says parameter has to be empty, the other says it is needed. So this is not being validated by the tool.
But I thought it might be interesting to have some kind of automatic, say, plugin or something that would, on the fly, some kind of compiler that would somehow validate this combination of rules, which could help early on, even if it's not validated.
So what I've forgotten to mention, those rules, they are partially validated on the fly, in fact. So easy rules, when you enter a parameter, this parameter is validated against itself, against its own domain. The check against all the different rules cannot be done on the fly, because these are way too many that you can evaluate it on the fly. So there are special trigger points within your configuration tree where you can do validation against, for example, an own module only or partition only and the subset, but you would not be able to validate on the fly against all the used domains every time you type or change anything.
But it might be possible to do modular approach somehow with pre-post conditions that could. I mean, we can take
it. It would be possible. In fact, yes, it would be possible. It is not implemented this way.
Thank you.
Any other questions? Thank you, Martin. So now we have our invitees, representatives. I would like to thank you again for staying with us until this late evening. So, Christina, thank you for coming. I will ask you kindly to present your organization, where are you coming from, and, well,
thank you. Thank you, okay. Hello. I am Christina. I am currently having 2 different jobs, which is nice. So most of my time I spend at Saab, but today I will talk about what I do on my other job, which is at Mälardalen University, MDH. It will be very short, even though it's late. So at MDH, we are not standing out in research for avionics so far, but hopefully this will change. There's a lot of initiatives going on, and we are forming a new research center, MARC, and we would like to stress that this is to rise both in the education program and also in the research domain. It is built on, we don't start from scratch, it's built on 3 existing groups, artificial intelligence group and the robotics group, and also the safety critical engineering group. And this has been strong research areas where we have long history, and since 2 years, I would say, MDH have started to employ people from industry, as myself and others, to get more strong into avionics as well as space. So this is what is really ongoing right now. Of course, so far we have come up with some strategic goals, as all new research area or centers has to have. And we are focusing on the engineering programs, actually, as much as the research part. We would like to be a recognized partner for industry. Of course, Saab is already on the boat, so to speak, but there is also good collaboration with ABB and Scania and Volvo Construction and Bombardier, very strong areas for embedded systems within this region. So there is a lot of good industry collaboration going on. Just 2 weeks ago, we got okay to start a new educational program. So this is not out yet, so actually I had some problem to finding the English title. In my next slide, I have to apologize, is in Swedish, because this is going on in Swedish. But this is a new a new educational program, 5 years, civilingenjör. It's a typical Swedish education. It's not like a bachelor and a master, but similar. So it's a 5 years program. And we will call it Master of Science in Engineering, Aerospace Engineering. So what I could say that is a little bit, I think, new and different is that the exam is not the same name as the program. So the exam is in dependable systems. So we are not focusing on structures, aerodynamics, but we are focusing on avionics, embedded systems, dependable systems. And we are using our domain, the knowledge from our domain, in order to form a very attractive program for the students. But then the examiner would be too small to say if it is our domain, even though there are many people here and we really like our work, but it's a small industry compared to automotive and train and so on, or telecom. But so really addressing this growing complexity in our embedded systems, where dependability is a big issue. And our industry is, I would say, leading here, because we do have fly-by-wire and it is safe. So we would like to use the opportunity to learn from how to develop and why we need to have all this specific formula and the regulation. Also the regulation part is very important. And this has come very far in our industry compared to automotive, for instance. They don't have certification authority. They don't have they don't want to look into our standards because it's too expensive. I think they will have to if they're going to have a drive-by-wire one day. We'll see. But so this is really exciting, and it will start next autumn. We will start with, hopefully we have many students coming to us. So this is the Swedish slide. I didn't have time. It's not that important, but we have formed a new program, and the coloring is just because we have been doing a lot of argument to make our case, to say that we are strong and that we are in the phase to take on this new challenge to start a new education. And in the green color is just programs already there. Of course, this is an engineering 5 years program. There's a lot of basic stuff everybody has to have, mathematics, physics, and mechanics, and so on. And then we have also some program going on from the embedded systems and from computer engineering and from the other programs, robotics. So these are the yellow ones. So we do some modifications. And then there are specific new courses that we will start, are also developing right now. So I will have a lot of nice work here ahead. This is the yellow one, targeting our domain, fault-tolerant systems or avionics. So we are not part in actually this currently from MDH. Saab is here, but I am an MDH person right now. So, but hopefully we will be a player in the next program. Yeah.
Well, you can take advantage.
Yeah.
Also sad.
Yeah.
You are the head.
Oh yes, yeah.
You can take advantage of that.
That was all.
Thank you very much, Christina.
Yeah. Thank you.
I think all of us are very pleased.
This is
This new master. And I will take the chance also to inform you that we have some training models in the format of video from Scala that eventually you can use. They are of interest for training. So regulated with the INA. So you can just see tools and this kind of certification. So different kind of models, training models that you can download it from Scala website. Okay. So you know about it. So, okay, thank you. So the next speaker,
Yes.
Ingo, so you can introduce yourself.
Okay. So good evening then. So my name is Ingo Sander. I'm associate professor from KTH Royal Institute of Technology and coming from the domain of electronic system design. So I've worked in industry 20 years ago, but I mean actually my view of the world at that time was that the design process just is, I mean you have a specification and then there are a lot of documents, and there are more documents, and you refine this document, and at the end of the day, things go into the hardware department, the software department, and then you integrate the whole thing, and then nothing works. So actually the problem, which looks extremely simple when it comes to the design process for embedded system, so it looks very simple. You have an idea, you want to make a product, you have a design process, and somehow you do it, but it looks for me like magic. I mean, somehow industry gets systems to work, but they a lot of verifications needed and so on. And the reason is, in my opinion, there is actually a lack of systematic design methodologies and tools. And we have actually, if you look at the architectures we use, the processors we get and so on, they are actually non-predictable. They are designed for average case performance, but not actually for worst case and so on. And especially if you do real-time systems, you have really, really big problems. The question is then actually, today we have already problems with complexity. So how do we do in 20 years or 15 years? I mean, when we design more complex systems, the architectures get more and more complex and so on. And we have heard very much during this workshop, we heard a lot of ideas how we can do it. But I mean, there are actually, in my opinion, what is needed is, we can use Agile, we can use this and this and this, but there is an underlying problem. And the underlying problem, how I view is, we have actually not good models, not good applications models, which we actually can analyze, so which are formal in a sense. We do not have platforms which give us service guarantees, so predictable platforms. And then, if we would have this, then we could have analysis methods which work on a formal application model and on a predictive platform with service guarantees. And obviously, if we want to get this whole thing into industry, what we need is some kind of industrial entry language. So that we can simulate our application model. Obviously, we shall verify it later. And then we also want to automatically extract these analyzable models, and they're using some formalisms done from, for example, research and so on, and apply it on it. So this is, so to say, what is needed. And we have worked since quite many years, actually, on a methodology which uses these things. But first, looking at this underlying thing. So I said already, the target platform is not really reliable. So most of them are done for average case performance. So we have things like caches, and they are difficult to analyze, especially, and so on, but also pipelines and things like that. So we could, we could actually use a scratch patch memory, and I think this is also often done in industry when you want to have a predictable system. Other problem which we have today, now we go to multi-core, we want to design real-time systems, and I think all of us know that when we have a shared memory, then actually the execution time of a program on CPU 1 is dependent on what is running on CPU 2, which means we have no composability, we have difficulties to use any formal method. If we change something in program 2, then program 1 will have it at different execution time. And obviously, we can change it by using dedicated resources, even for the communication, so that we actually, for example, use the time division multiplex bus. So I think in avionics, this is quite well understood, these things, not in all other industries. But so this is, so to say, the one aspect, the platform. But then also, if you look at the higher level, we would like to have actually models which we can analyze, where we can actually do where we can do things with. Now, look at an example here. So we have here following a kind of system, which is a very simple application. So it's an abstract model now. We're assuming we have one process A, one process B, and one process C. And this A process, does some functionality. Whenever it executes, it produces one token. Now, this B process, it always takes 2 tokens when it executes, and it produces 3, and the C process always takes 2. Now, if the designer is not aware of this, the theory which we use in our research, which is called models of computation, then actually what would he do? He would say, oh, there are 3 tasks, A, B, and C. Perfect. So I use a real-time operating system, and then I connect this task with a message queue, for example. And of course, he will be able to build a model, not only a model, but it will be a system, the software, and the software will also work. But the problem is that actually the real-time operating system consists, first of all, an overhead. You do not need it here, which I will soon show you. So, sorry. And then also, you have buffers here in between. Now, how large shall the buffers be? Well, for this simple example, after some time, you know. But if the example is larger, it will be difficult, right? So you don't know how large the buffers are. So what do? Well, industry, and I've talked with many people, what you do is you put a safety margin. How large? I don't know. The industry does not know, so make a larger one. Fine. So we are all happy. But you get 2 overheads here. Larger buffers and a real-time operating system. Now, if the designer instead would know about models of computation, so this is inefficient, obviously, then actually, you take a course at KTH or somewhere else, where they have discussed synchronous data flow, which is already from 25 years ago. Then actually, so to say, you can see that here you can do a static schedule, right? You just have a static schedule given here, and then you can also, because it's static, so you can simply calculate the buffer sizes. Okay, no real-time operating system, it gets even faster, no safety margin. So very good, we're all happy. So we should use this. But does the designer know anything about models of computation theory? No, the designers don't know anything. Most of them, at least. And obviously, a university could do a better job here. But, so what do? So what we want is that the designers specify their models using this kind of model of computation theory, and there are several models of computation, and at the same time should have an easy time, should use this nice language. So what we did in several, at KTH and several European projects, is that we came up with a foresight, which is called formal system. It should be formal, and then, of course, it should be system, design. And here the designer specifies a model, system application model as a set of concurrent processes. And these concurrent processes, in order to do this, he has to use the foresight libraries, and they come with some rules. So they follow the models of computation. So the thing is then that if the designer follows this approach, and he has to, right? Then actually we can extract automatically this process network and can work on it, so analyze it. So let's look a little bit on it. And we have actually now, it is implemented nowadays in System C, which is an IEEE standard language. So what do we do then? We have a model, great, and so on. Now we want to get real-time software, as a software which satisfies real-time requirements. So we have our model, this model, designer uses foresight library, and so on. It can simulate this model and so on. Fine. Second, we have a predictable architecture. This is important. And it's predictable not only that we know how long time, for example, a process P4 takes on CPU 1, but we also know how long the communication time between different nodes are. then we have constraints. We look now on first only on real time, but if we would have power models, we could also look on power efficiency. And then given actually not only, you can even have more than one models, a predictable architecture and design constraints for each of these models, then we conduct design space exploration, actually where we sort of say try to find an efficient mapping. So of course many different mappings are possible. We try to find a mapping that is efficient and where we satisfy the design constraints. And then the second step, last step, is then, given we have this mapping, we produce the software, so to say, automatically, because here we get the mapping, we get the schedule, and here, since we use System C, which is a C-based language, we actually get also the C functions. So we synthesize this into software. Not everything of this is implemented, or not the whole flow is not just now not integrated, but many steps of it are, and we're just working in several European projects with this. So just from the designer's point of view, it's the following. The designer models an executable System C model, uses the Foresight libraries. You automatically extract the process graph XML plus C. Then you make design space exploration, and then you actually get the code generation for individual processors. And I think, and we have here, I think this slide is a little bit too complex for the short time I have. Just saying quickly that actually that you require from the platform that you have communication primitives for message passing and service guarantees. This is what we require. Otherwise, we cannot give guarantees. All right. I want to say a few words of what my colleague is doing, sits next to me on the ÖBAG, and which we also use as a typical target platform for our design. So this is a NSG, NOC system generator. A network on chip is, so to say, you have several processors which communicate via a packet switch network, you can say. And here we have, we can specify different sorts of, for each node we can specify the C code, and we map it to different processors, and then we can generate a full system. And the nice thing with this tool is that it's extremely flexible, because you can just, I want to have here 5x5 network on chip, or 3x2, and so on. And if you want to know more about this, I just give you can later go to Jonny, and I think you can even show something, right? All right. Now, what is the state and what are we doing? So, I mean, we use this not in the avionics setting, unfortunately, maybe. We have KTH and Saab have so to say initiated or have an agreement that we should work together. So we're discussing just now with Saab, in particular with Ingemar, how we can do things together here. And so the ongoing work is actually, we've tried to complete the flow, right? We have a nice modeling library. This works. It's publicly available. You can download it, work with it. Then we have also the first version of the design space exploration, where we use constraint programming as an optimization method. And we work on several backends. One backend is network on chip, which is, and then we have also hardware, VHDL, software, C, C++, and also CUDA backend. And Foresight is actually active just now, has used an earlier EU project before. Now it's used in Contracts and EMC2, which are running both of them. And both of them are projects in the area of mixed critical systems for multi-core and real-time requirements. So with that, I think I finished my talk. And if you have questions. Yes?
I think it's I have a question. Could you please go to page number 8? My name is
8? Yes.
So my name is Eric Schalk. I'm from Airbus Germany, working for the data flow and for Toolchain, together with TU Hamburg, by the way. My question is, what are you exactly modeling in the FORSUD model? Is it the resources and the data flow before you program it, or what is it, what you model?
No, we use actually, so we model the functionality of the system. So you can see it's the same, like the algorithm, you can say, or the system functionality we model. And we model it as a concurrent process network, right? So each process has a functionality, and it has the interface which complies to the model of computation. And these are then run, these you can then execute with System C. So the resources, so to say, or so the platform is modeled here, right? And then during this design space, then you map this model onto this, and then. But maybe I've not misunderstood the question.
No, it was exactly the question.
Okay.
Because the question was whether the function is separated, modeled, and the hardware resources and the hardware flow is separated.
Yes, they are separated. So if you change, you can sort of say change the architecture as an example, and then you get a different. Obviously, the design space exploration will produce a different mapping, right?
And this you do automatically.
The design space exploration is now running. We have now had the paper date, which is the Design Automation Conference, a big one in our area. So where we had actually several applications with different requirements, and an architecture which was a TDM. It was a TDM multiprocessor with TDM bus. And for this, we then calculated the mapping. Yes. And what is done here, what is already there, if you have the model, if you have your, so to say, for example, you have a system model, you can automatically generate this graph, right? And these things. So there is there's still some connections which are missing. I mean, always so, but I mean, I can talk to you later if you're interested.
Okay. Thank you very much. I have another question. What is the application on aeronautics side? Is there some areas where you
No, we discussed just now with Saab, actually, and so we try. Okay. So Ingemar should say a little bit, but we have not really started. We just discussed, sent him 3 days ago a proposal.
Okay, that's
now we go, but we had quite some discussion before.
Okay, thank you very much.
Any other questions? Ahmed? Thank you. Thank you. Holly Shopping?
Yes. Thank you. Right. So, thank you for making it until now. So it was a good evening. Let's hope it's not good night yet. In fact, when I heard about the workshop, I intended to come because I thought I will find several interesting discussions and presentation. It was the case because there were many presentations about formal methods and verification, which is a little bit what I work on. And then I was asked to give a presentation about the group of what our group does. And so that's why my presentation has as a title, Automatic Verification at SLab, which is the group where I work in Linköping University. My name is Ahmed Rezin. I'm an assistant professor. So, right, the background. So I will introduce a little bit the activity of the group where I am, and also mostly the kind of research I do. So bear with me. So SLab is a leading group in embedded systems here in Linköping. There are 2 professors, 2 assistant professors, 1 postdoc, and about 10 PhD students. They work mostly on system-level design optimization, hardware, software co-design, scheduling, schedulability, fault tolerance, architecture and techniques, low power design and voltage scaling, software and chip testing and silicon debug and validation, and so on. I myself work mostly on model checking and software verification. This is what I am here a little bit to introduce. So this might seem to you to be a bit specialized, to be maybe not very well adapted to avionics. But the point here is that in order to verify these systems, we had to develop new techniques to tackle, in fact, systems that could not be tackled before, to programs or hardware verification issues that could not be tackled before. And we hope that we can adapt them to, say, avionic systems or safety-critical systems. So myself, I work mostly on extending automated verifications to systems that might have arbitrary many states. Arbitrary many states like infinite many states. Of course, every instance will have a finite number of states, but the point is that sometimes, often in fact, instead of reasoning about what about a system with 2 states, 3 states, 1,000 states, so on, this makes it more complicated than actually reasoning about arbitrary many, because then you are obliged to reason using symbolic methods, using some calculus or some predicates, or just reasoning. The reason why the protocol, the program works, doesn't have to do with how many elements you have. It should work for any number of states. And sometimes capturing this reason actually makes it possible to verify. While if you would incrementally go from one size to another, you will not manage to do it. So what I do mostly is that I extend software model check-in to arbitrary many concurrent systems or distributed systems, heap manipulating data, programs, and cache coherence protocols, and so on, weak memory models, something. And so here, I will give some examples of such systems. Now you are wondering, why infinite state system? What do they stem from? Where do they come from? So suppose now you have such a program. This is just a model, but it could be extracted from the code. Here you have, for instance, two processes. One of them, they can choose not deterministic to either read or write. And the idea is that when one of them is writing, the others cannot read. It's exclusive. There must be at most one writing. But there can be as many processes that read as long as there is no writer. And there is a small code here that involves, in fact, a number of logs. It involves an integer variable. And there are some tests and so on. And the point is, can they, for instance, violate mutual exclusion? This is the typical example. Of course, you can analyze more complicated more complex situations, properties. So what you do here, one possibility is actually to test. Okay, I have 2 processes. I go on. Okay, what are I do full space exploration if you wish. But then the idea here is that you, instead of generating tests, you want, in fact, to explore the whole behavior. Explore need not be concrete. It can be symbolic. We'll get to that. So here the idea is that you have a program or a model. You have a specification in whatever form it is. It could be LTL, or it could involve time, or it could involve probability, and so on. Then you have a verification engine here, a model checker, that in fact gives you a counterexample, which is actually very useful when you are analyzing your system. Or you get, which is maybe less interesting, a stamp that indeed this property holds. Because actually what you are after is really these counterexamples that actually will give you a hint of where are the bugs and so on. This is the more interesting part. Now, the thing is that this was applied, of course, we are not inventing model checking. Some people got the Turing Award for it. But typically, these are adapted for finite state system, communication protocols, drivers, where you have a lot of control. But many systems, in fact, are not finite in nature. And what you want is still to apply this formalism to it. And what you are obliged to do is that since they are not finite, you cannot just concretely go through all the state space. What you need to do is actually to explore the state space with new techniques, symbolically representing and abstracting this. But still you want to state, you can think of it as another way of debugging when you get a counterexample, or you can think of it as, in fact, a certification, if you wish, that, whatever the path is, you will not violate the specification. So why infinite? Well, the thing is that we had 2 processes. Now, what about 3? What about 4? What about if you have a system where we spawn, depending on the run, we spawn more and more processes? So this can generate arbitrary many processes. And then what do? You cannot stop the plane and go and check, what about 57? Of course, when you have in avionics, you avoid spawning on the run. But you got the idea. There are systems where you have this, in fact, size that can be arbitrarily large. And the reason why this protocol works is because, in fact, this counter is counting how many readers you have. It's as simple as that. If you count how many readers you have, and you maintain this, then you know that you will not violate mutual exclusion. You don't have to try 2,978 threads in order to check that. So the idea is to extract the reasons why it works as automatically as possible. Of course, push-button technique is something ideal there, but we will not get there. So what we want is to have a tool that helps you as much as possible. So for instance, so this is about that. This is one reason why you might have infinite state systems. There are many other reasons. We'll look at some of them now. But the idea is that here, still, the problem is very difficult. It's undecidable. It's not just intractable. You cannot do it. So what you do is that you try to approximate in order to get good results. And the challenge is to find symbolic representations and abstractions that work often. This is a work that we just got accepted, where in fact analyze such systems and even more complicated ones where you have arbitrary mini threads that spawn each other, they share variables, they in fact have their local variables that can be integers, they update them, they have locks, compare and swap, you name it. And the idea we do here is that in fact we use predicate abstraction. Some of you are familiar with it. That is, we generate on, somehow in the beginning we say, okay, we remove all the details. Do we still satisfy the properties? So the idea is to have over approximations that are sound. If still we, after removing all the details of the program except the control flow and so on, and we manage still to show that the program is safe, then we know the program is safe. If it is not the case, we'll need to add more predicates that will track more details. So the idea here is, you see, these are classical results, but we apply them, in fact, to challenging systems. Threads, arbitrary mini threads with infinite data that are integers and so on. And in fact, the idea is that we can go on forever like this, trying to verify, but if we manage to verify or to exhibit a counterexample that it is a real counterexample, or in fact, there is no run that actually violates mutual exclusion, for instance. That's one way to do. Another application is these models of cache coherence protocols. Okay, I have cache coherence protocol that says how I should change the state of my cache lines and so on, but you can do it for 2, 3, 4 caches, but I mean, multi-cores now will have more and more cores, and then what you want is still to show that this protocol somehow, how do you move from the invalid to the shared to the exclusive state and so on, whether it does respect cache coherence or not. And then, again, these 2 or 3 or 4 here, they are quite simple systems because they are finite state individually. But when you take arbitrary many caches, and the reasons why they work are, again, very simple. So there is no need to actually try forever. I mean, one can capture this automatically again. Other applications include, for instance, this is a challenging thing, which I understand that the avionic industry avoids, to have heaps and to have, you want to avoid to have dangling pointers. You want to avoid to dereference null pointers. You want to make sure that if you start with a sorted list, that after the running this program, you will end up with the same sorted list, that you do not have cycles and so on. These kind of properties are quite challenging. And still here what we did is, for instance, to come up with an abstract domain that in fact captures this for singly linked list with data and so on. And that can in fact prove several such programs to be indeed correct. Other applications include, so this is even more crazy. If you thought that one was strange, this is even more, because this is in fact when you have multi-core systems, you have this lock-free algorithms and fine-grained lock-free algorithms and so on, and that are based on, so you try to avoid having locks. What is happening here? Okay, thank you. Yes, that's what it is saying, so I'm going to speed up. So here, the properties you want to check are even more complicated, because it's not just about reaching this or that, it's about linearizability, whether no matter how you interleave these push and pops, for instance, in a stack, you have a coherent serializable way to look at it. You can make sense of it somehow in a sequential world. So this also, we verified such systems, and to finish the examples, we have memory model aware techniques, where in fact, when you have memory models, we can run in multi-core systems. So you have this, that the threads, when they are running, they do not see the updates to the main memory in the same sequence. And what we developed is a technique, in fact, for certain models that is complete, for certain models that is always an over-approximation, where in fact you can, that is sometimes an over-approximation in certain conditions, that in fact you can show that, yes, indeed, that property is not going to be violated even when you have a weak memory model. And if it is violated because of the weak memory model, then we automatically insert fences, in fact, in order to retrieve the sequential consistency model and so on. So these are things that have to do with these infinite models and so on. But I hope that this triggered some interest and that we can pick some discussions. So thank you, and hope not good night yet.
But I raise a simple question. For what is it exactly? Is it good for WCET calculations, or
Right.
What I understood is a
Right.
predictable behavior. You are
Right.
introducing techniques to predict behavior of different software architecture.
Right.
Is that true or not?
Myself, I do not work on worst case analysis, unfortunately.
Yeah.
And I know that here it is very important. But some people actually use similar techniques like abstract interpretation and so on in order to, in fact, establish worst case. So this is a little bit related to abstract interpretation and to where you over-approximate and you try to have a sound bound. I do not do that. But of course, it doesn't. Some people actually in my group do that. So for instance, they would use symbolic executions in order to, in fact, find what is the worst case to get a better bound, for instance. But then they do not look at infinite systems. They would try to go for a nice architecture, somehow for a nice model that they can analyze.
For what are you apply this technology in detail?
For myself, I apply it more to program software in general. So I try to pick such hard problems. Usually they're not very big, but they're enough complex in order to be very challenging. Okay. But it can make sense, in fact, to look at finite instances and use, because we use technologies like SMT solvers, interpolation, and things like that in order to explore. So it could make sense, of course, to apply it for worst case. But I do not do that, so other people do.
I can only say from airframer point of view, this makes sense to investigate, because WCT is always a critical item that has to be done at the end of the certification phase.
Right.
And we have to guarantee that processors are not overloaded by the application integrated on IMA. Right. And the problem we have always is to show and to analyze and to measure and to demonstrate in front of the authorities that we are never overburdened the processor. Right. So if you have technology that predicts the situation in a processor and say you are not overloaded in the moment, would help a lot.
Yes. Thank you.
I think some of these techniques, and correct me if I'm wrong, but some of these techniques could actually be applicable in the avionics domain to the multi-core problem that we have been discussing, I believe, in our studying. Because if you speak about a 4-core system and you just apply it to a single partition and you have a set of processes, you will have for sure a probability of concurrent system access. So you can solve that, or I would imagine that you could solve some of the problems that could arise through these methods.
Yes.
Yes?
You could formulate certain problems using this, yes.
And when we speak, for example, on a quad core, if we speak 20 years, 30 years from now, it's not that difficult to imagine that you could have a 64-core or a 128-core system running. So that the exponential difficulty of it increases. So.
Yes. But of course, we are kind of at the research frontier somehow. So so right now we are looking at problems like, can I violate mutual exclusion? But here the problems you are looking at are more like about scheduling. Can I violate this worst case and so on? There are people, and I mean, these are interesting questions that should be answered, in fact. But there is a good playground here.
Even for certification, if we consider multi-core, not just for the worst case execution time, but also in terms of the potential of concurrent collisions and concurrent collision analysis. It has to, if we want to certify a multi-core system, we have to take that into account. I don't see any other way.
So your investigations are related to multi-core processors?
So for instance, typically these memory models, weak memories are really for multi-core, for instance. But having several threads that are running, this one, for instance, is not. It is of course more acute when you have multi-cores, but you can see it on. It is a bit independent on which. Yeah. Thank you.
So, thank you very much. I think we reached the end of this academic workshop. I really would like to thank very much to our guests for staying here with us until this late in the evening. I think it was quite productive in terms, we could see by the questions that has been raised. I think there was a good interaction during the coffee break, and the most important thing is really that to continue this contact that we just started and try to find opportunities for future collaboration, at least during our project. We are pleased to provide you the kind of information that you will need, that we can also provide to you. So thank you very much. I think, I don't know if our coordinator manager wants to say something.
Thank you so much for being there with us.
I think we had a very good package of topics dealt here and of quite industrial interest. We could see by the industrial questions that has been raised here. So, again, thank you very much.